How's it going, guys? Today in this video, we're going to be going over solving a system of a linear quadratic system. So what that means is that we're going to have a system of equations, but in this case, it's going to be one linear equation and one quadratic equation. And we're going to solve it. And when we say, well, we're going to solve it, what that means is we want to figure out how many intersections both those equations have. So if you look at these two graphs over here on the right, we have a straight line and we have a quadratic, right? So there's going to be three different ways for the quadratic and that linear line to actually intersect. All right, so let's say we have our parent function of the quadratic right there. We could have one line that goes straight across just like that, and it would have two intersections. We could also have a quadratic. Let's just stay with the parent function right here, the parent quadratic, just like that. And we could have our straight line go right over the x-axis to only touch the quadratic right at its vertex. Or let's just pretend that's only its vertex. And we'll only have one intersection. And you could have a relationship kind of like our quadratic and our directrix, where they don't intersect at all. If they don't intersect at all, we have zero intersections. And if we have zero intersections, we can also say that that system has no solution. If you don't have any intersections, we have no solutions. If you have one intersection, we'll only have one solution right at that point. And if we have two intersections, we have two answers at both those intersecting points. So if we go on here, we have some notes. So solving linear quadratic systems graphically, that's probably the most straightforward. We're just going to graph both those equations, and we're going to see where they intersect. And both those points are our answers. All right, the points where they intersect are going to be our answers for the problem. If we're solving a linear quadratic system algebraically, there's going to be two different ways to solve it algebraically. We can use elimination or we can use substitution. If we're using elimination, what we need to make sure is that everything lines up on top of each other. So the constants are on top of the constants, the y's are on top of the y's, and we need to make sure the x's are on top of the x's. All right, so we need to make sure everything lines up like that, so when we subtract them, we can get rid of those y's. Then after we do that, we're going to have one equation with only x's, so we're going to rewrite that quadratic equation into standard form, make one side equal 0, and then we're going to solve that quadratic however you like. Factoring will probably be the easiest if you can actually do it that way. Some quadratics you cannot actually factor it, and you have to use the quadratic formula or completing the square. But 9 times out of 10, I would say even more often than that, the quadratic formula will be much, much easier than doing completing the square. You could also do it by substitution. With substitution, we'll just set both equations as y equals. Then you'll plug one equation into the other. Since both y's are equal, you take what one y equals, plug it into the other equation, and then you'll have one equation with only x's. We'll do the same thing we said before. Sorry, we do the same thing we said before. Make our quadratic, equation, put it into standard form, have 0 equal one side, then solve it however you like, completing the square, quadratic formula, factoring if you can. Whatever you like, just solve it out for your x value. But once you have your x value, and this goes for both these problems, once you have your x value, you have to plug it back into either equation to solve for our y value at that point. All right, so there's going to be one extra step because we need a point, not just an x value. So once you get your x answers, you have to plug them back into the equation to solve for your y term. All right, so let's actually look at a couple of examples. So number 1, we have y plus 3x equals 0, and y minus 6 equals negative 3x squared. So we're going to, if we're trying to solve this graphically, we're going to set both those equations, equal to 0, and we're going to graph it that way. So for y plus 3x equals 0, we just subtract that minus 3x, or that positive 3x, to get y equals negative 3x. So in this case, we have y equals negative 3x. Our y-intercept here is just going to be 0. Remember, these are in the form y equals mx plus b. In that b term, that's going to be your y-intercept. So if we don't have one, our y-intercept is just 0. And that m term, that's our slope, our rise over run. So our rise over run in this problem is -3. So that means we're going to go down 3 over 1. So go ahead and just plot that. All right. So you should get something like this. All right. So the b term, that's your y-intercept, that's where you start. And then the n term, that's going to be your slope, your rise over run, so you can get the rest of the graph just like that. When it comes to solving the quadratic, well, before we actually go ahead and graph it, we're going to set it as y equals. So I'll add 6 to the other side to get y equals -3x squared plus 6. So remember that quadratics are in the form y equals a times x minus h squared plus k. So our hk is our vertex. So in this problem, the y equals -3x squared plus 6. Our h is going to be 0. Since we don't have any parentheses or an h value, it's assumed to be 0. And our k value is 6. So our vertex is at 0, 6. And now to solve for the rest of the quadratic, I'm going to make an xy table. All right? So we have an xy table, and we're going to put our vertex right in the middle. So 0, 6 is right in the middle. And I'm going to choose 2 points to the right and 2 points to the left of that vertex. And I'm going to choose the very first 2 numbers to the right, so 1 and 2. And the very first 2 numbers on the left, so -1, -2. So what I'm going to do is plug in these x values into my equation. So if I plug in 1 into the equation, I get y equals -3 times 1 squared plus 6. -3 times 1 squared. 1 squared is 1. 1 times -3 is just a -3 plus 6. Gives me a +3. So if x is 1, we get a +3. So we can go ahead and plot that at 1, 3. And remember that a quadratic is always symmetrical about the vertex. So I can flip over that 1, 3 point to the other side of the vertex, and I'm going to get the other points. So I guess it's kind of like it's mirror points, reflection. So the reflection of 1, 3 is going to be -1, +3. That's its reflection to get to the other side. So on the table, we have -1, +3. And now for x equals 2, we'll do the same thing, plug that in. Y equals -3 times 2 squared plus 6. 2 squared is 4. 4 times -3 is -12 plus 6 will give us -6. So we have the point 2, -6. And we'll do the same thing. We can mirror it over the vertex or flip it over the vertex, reflect it, whatever you want to think about it. But either way, we're 2 away from the vertex to the left. So if we go over 1 and 2 to the vertex, we go over another 2 to get to -2, 6. -2, -6, sorry, to get our other point of the vertex. It's just much easier than solving for 4 points altogether. It's much easier to just know that quadratic, sorry, I have a reflection over the vertex or symmetrical over the vertex, so you can figure out your other half really, really easily. So we have our 2 graphs graph. So what we need to do now is just find their intersections. And I see that intersect right here at 2, -6, and also at this point, -1, +3. So at 2, -6, and then -1, 3, those are going to be our solutions to the problem. That's where they intersect. That's where our system of linear quadratic systems have the same x and y terms. So that's our solution to those problems. And now if we're going to do the same problem, the same exact problem, same exact equations, we want to do it algebraically. I'm going to erase this and make a little more room. What we're going to do is we can do this by elimination or substitution. I'm going to show elimination for this problem, and for the next example we're going to do together, I'll show that with substitution. So for this one right here, we have y plus 3x equals 0, and y minus 6 equals -3x squared. So remember, you want to line up the y's and the constants and the x's all on top of each other. So it's 3x. I'm going to move to the other side to have it over the -3x squared. So when I rewrite this, I'll get y plus 0. I still want a placeholder of 0 to have something over that constant of negative 6. Will all equal negative 3x. And then I have y minus 6 equals negative 3x squared. So I can see that everything's kind of lined up. The y's with the y's, the 0 with the negative x, and the 3 with the 3, or sorry, the x's with the x's. Everything's kind of lined up on top of each other. So I can go ahead and just subtract these numbers and get my new equation. So y minus y is going to be 0. 0 minus negative 6 is a positive 6. That's another reason why we put that 0 there, so you don't forget to change the sign of the negative 6. Since 0 minus negative 6 just changes the sign to positive 6. And that's all going to equal negative 3x minus negative 3x squared. We cannot combine those x's because one's a regular x, the other one's an x squared. So we're just going to rewrite it as negative 3x minus negative 3x squared. And when we do that, we end up getting 6 equals negative 3x plus 3x squared. I'm going to move the 6 over because I want this in standard form. So I want it in ax squared plus bx plus c. And I want 0 being on one side, so I can actually solve it. So when I move that 6 over, I get 0 equals 3x squared minus 3x minus 6. I move the 6 over, and I rearrange that right side to have an x squared be first. So from here, I'm trying to word this correctly, but from here, you could use the quadratic formula right away and solve for your answers. You could do that. Another easier way is to see that we can actually reduce this all by a factor of 3. We can divide both sides by 3, because when we do, 0 divided by 3 is just 0, and the right side becomes x squared minus x minus 2. 3x squared minus 3x minus 6, each one of those are all divisible by 3, so I can reduce it and make it much simpler. And instead of having to do the quadratic formula, since my a is a positive 1, I can just find factors of my c value, which is negative 2, that add up to my b value of negative 1. So in this case, negative 2 times positive 1 gives me negative 2, and negative 2 plus 1 is negative 1. So my factors are negative 2 and positive 1. So I can rewrite that as x minus 2 times x plus 1. That's my factored form of x squared minus x minus 2. And then I'm going to solve each one of these for x. I'm going to set both parentheses equal to 0 and solve for x. Or you could think about it just changing the sign, whatever works for you. But our answers here are x equals 2 or negative 1. Those are our two x value solutions. So what we're going to do from here is take these x values and plug them back into our original equation. Whichever one you want to use, it doesn't matter. Usually the linear equation will be much easier. So we can use this one right here, that y equals negative 3x. We can use that equation right there to plug in our x values to see what we get, to get our y values, sorry. So we're going to use the equation y equals negative 3x. So when x equals, not negative 2, but positive 2. So when x equals positive 2, we'll take our x value, plug it into that formula to get y equals negative 3 times 2, or y equals negative 6. So when x equals 2, our y is negative 6. That's one solution. Now we'll do the same thing when x equals negative 1. So when x equals negative 1, we'll plug it into the same formula. So y equals negative 3 times negative 1, or y equals positive 3. Or our answer is negative 1, positive 3. XY. And we can see that this answer right here, the 2 comma negative 6 and negative 1 comma 3, are the same exact answers we got when we solved it graphically. So it's the same exact answer. We'll get the same exact thing because it's the same exact problem. We should get the same thing. And that's what we got. All right, so we're going to go on to the next example. So here on number 2, we have y plus 1 equals 1/2 times x minus 3 squared. And the other equation is x minus y equals 6. So if we're trying to solve it graphically, we'll do the same thing. We need to have both of them as y equals. So for the first one, I'm going to subtract 1 over to get it as y equals. So y equals 1/2 x minus 3 squared minus 1. And the second equation is x minus y equals 6. So x minus y equals 6. I'm going to solve for y. So I'll subtract the x over. So negative y equals negative 6 plus 6. Multiply everything by negative 1 to get y equals x minus 6. So y equals x minus 6. That's going to be my other equation. So I'm going to go ahead and graph both these equations. I'm going to start with the one in blue, the linear one, because it's just a little easier to graph. So my y-intercept is negative 6. Remember that b value, that's your y-intercept. And I have a slope of 1, so I go up 1, right 1. So let's keep going. So you should get something like this. All right. So that's what your linear equation is going to look like. And now we're going to figure out what our quadratic is going to look like. So we have y equals 1/2 times x minus 3 squared minus 1. So remember what our formula of the vertex of the quadratic formula is. I posted it in the previous slide. Remember our vertex is hk, so it'll be 3, negative 1. That's our vertex. Let's actually say consistent with the colors and make this red. So 3, negative 1. That's going to be our vertex. And we'll do the same thing we did before. Make an xy table. I think this is just the simplest way to go about it. So 3, negative 1. That's our vertex. And we'll pick 2 points after it. 4, 5, and 2 right before it. 2, 1. And we only need to solve one pair of these because remember from before, since the 4 and the 2 are just as far away from 3 as they are from each other, they're gonna be mirrors of each other. So we plug in 4 into the equation. We get 1/2 times 4 minus 3 all squared minus 1, or 1/2 times 1 squared minus 1. 1 squared is just 1. So 1 times 1/2 is 1/2, minus 1 is negative 1/2. So when x is 4, y is negative 1/2. So we can plot that. And I know the reflection of that, the mirror of it at 2, will be the same thing. And now we'll do the same thing when x equals 5. So 1/2, 5 minus 3 all squared minus 1. 1/2 times 2 squared minus 1. That 2 squared is 4. So 2 minus 1 is just 1. So when x equals 5, y equals 1. And we know since 1 is kind of the reflection of 5, the mirror of 5, when x equals 1, we'll also get 5. So we can plug those in. And we get a graph that kind of looks something like that. So what we can see here is that they're never really going to intersect, right? The blue line is going to keep going at a constant slope of 1, but the parabola, the further away it gets from the vertex, the steeper it gets, or it just keeps shooting up faster and faster. So the faster it shoots up, the further away it's getting from the linear line, or in other words, it's just never going to intersect. So if they never intersect, there's no solution. However you want to write that, no solution, no n/s, just know that there's not going to be any solution to this problem. All right. So now we're going to do the same thing, but we're going to do it algebraically. So I'm going to erase all of this to make myself a little more room. And like I said in the previous slide, this one I'm going to do a substitution. This is to show you the 2 different ways, and you can choose whichever way you like more. It doesn't really matter. Let's do the same thing. So with substitution, we want both equations to be set as y equals. So luckily, I already have that over here. So I have y equals 1/2 x minus 3 squared minus 1, and y equals x minus 6. So remember, we're trying to find out what our x value would be when these y's are equal to each other. So we're assuming both these y's are the same. So that means when this second y equals x minus 6, this first y is going to equal the same thing. So if this, so those y's are the same, so I can replace that first y with what the second y equals, because they're the same y. So the second y equals x minus 6, the first one also equals x minus 6. So I can actually rewrite this as x minus 6 equals 1/2 x minus 3 squared minus 1. All right, so x minus 6 equals 1/2 x minus 3 squared minus 1. That's what we have. And now we're just going to try to put this into standard form. So we're going to add 1 to both sides because I want to isolate this x minus 3 squared to make sure, so I can actually FOIL it out, and I can put this in the standard form a little easier. So I'll add 1 over to get x minus 5. That equals 1/2 x minus 3 squared. And then from here, I want to get rid of that 1/2. Anytime you want to get rid of a fraction, do not divide by the fraction, multiply by the reciprocal. It's always easier to multiply. So multiply by its reciprocal, and reciprocal just means the fraction flipped upside down. So we have 1/2, we're going to multiply by 2. All right, so that's its reciprocal. It'll be 2. So I'll multiply both sides by 2. So the left side becomes 2x minus 10. And this 1/2 and 2 cancel out. And I'm left with x minus 3 all squared. So 2x minus 10, that'll equal x minus 3 times x minus 3. Right, I want to FOIL out that x minus 3 squared. I don't want it in that form. I want it in standard form. So I'm going to multiply, or I'm going to FOIL out x minus 3 squared. So I'll distribute out this x to get x squared minus 3x. And distribute out that negative 3 to get another negative 3x plus 9. That all equals 2x minus 10. So what I'm going to do now is I'm going to start adding my terms and putting one side equal to 0. So if 2x minus 10 equals x squared minus 6x plus 9, I'm going to add 10 to both sides and minus 2x to both sides. So the left side becomes 0, and that's going to equal x squared minus 8x plus 19. So if one side equal to 0, and I have my other side to be my standard form of quadratic, the ax squared plus bx plus c. So now I'm going to see what I can do to solve this problem. I cannot reduce this anymore. There's nothing I can do to simplify it anymore from here. I cannot factor it, which is usually going to be the easiest way to solve these problems. I cannot factor it. There's no factors of 19 that add up to be -8. So my last two options are going to be the quadratic formula or completing the square. And I don't know if you like the quadratic or completing square. I just think it's going to be a lot harder to do that than the quadratic formula. So I'm just going to do the quadratic formula, keep my life as simple as possible. So my b value is -8. I plug that into the formula. So we get 8 plus or minus the square root of 64 minus 4 times a times c. Right, 64 goes for b squared. 4 times a is 1, or a is 1, sorry. So 4 times 1 is 4. And 4 times our c value is 19, or 4 times 19 is 76, all over 2. And I can already kind of see that this isn't going to work out because 64 minus 76 is a -12. So I'm having to take the square root of a negative number, which means I'll have an imaginary number. And so if I have an imaginary number, that means there is no real intersection. The only time that the x's and the y's equal each other in this system of linear quadratic systems is when they don't actually exist, which doesn't really make any sense anyway. It's just saying that there's no solutions for this, no real solutions anyway. So we just say there's no solution. So in this case, there's no solution, and that's going to be our answer. There's nothing to solve for our y terms in this case, because if there's no solution, there's no reason to solve for our y. All right. So anyway, guys, that's the video. I really hope this was helpful. If you have to rewatch it a few more times, that's perfectly normal. This is not. I don't want to say it's hard, but there's a lot going on. So take your time, do some practice problems with it. The more you practice this stuff, the easier it's going to get.